Hi, this is John Whitaker for the graduate level probability class, and this is our 28th video lecture. And during this lecture, what I want to do is do an example that has to do with the corollary to the compound random variable identity. So that corollary, I want to do an example to that, where we're looking at the compounding distribution being Poisson. And then we're also going to prove a fact that's similar to something that we proved during video 27, where we have that random variable that has the probability relationship to another random variable, that is the probability m equals to n is equal to n times the probability n equal to n of the expected value of n. And then if we're going to say if n is binomial, then what can we say about m minus 1? And so we'll have a fact about that and do an example where we're using that corollary to the compound random variable function, compound random variable identity, and where the n is binomial. So that'll be the things that we do today. Okay, so as we get started, it looks like the video is a little bit fuzzy. I'm sure we'll be back in focus. Let us remember the identity that I'm referring to, the corollary. So here's the formulas that we have. The probability that S of n equals to 0, that's the probability that n equals to 0, and the probability that S of n equals to k, well, that's 1 over k times the expected value of n times the sum as j runs from 1 to k of j, alpha sub j, and then the probability that S of m minus 1 is equal to k minus j. So that was the corollaries fact. I'm not the conclusion. I'm not writing up the conditions. That's what we're using right now, going to be using. And so as an example of this, it says let S of n be a compound random variable with n being Poisson, with mean lambda equal to 4. We're going to let P of x of I equaling to 1/4 for I equal 1, 2, 3, 4. And what we're going to do is find the probability that S of n is equal to 5. And we're going to be using this and the fact that n is Poisson, so that m minus 1 is also going to be Poisson with parameter lambda. This problem is going to emphasize a kind of iterative process, and using this formula, it's going to emphasize it, but there's a little bit something that's hidden there that the next example we do will bring to light. This is our problem. Now look, the sequence that we have is x1, x2, x3, so forth, but all the way up forever, x of 10, x of 50, x of million. And here it has the property that x of I equaling I is 1/4 for I running from 1, 2, 3, 4. Let's explore that a little bit. Make sure we understand what our sequence is. Okay, so here's the solution. Since S of n is a compound random variable, then we have a sequence. x of 1, x of 2, and so forth forever, of independent and identically distributed random variables and since in our problem the probability that x of I equals to 1/4 for I running from 1, 2, 3, 4, just those, then then, here's what we have. X of 1 equaling to 1 equals to 1/4. X of 2, probability, that's wrong. Should be probability. The probability that x of 2 equals to 2 equals to 1/4. The probability of x of 3 equaling to 3 equals to 1/4. And the probability that x of 4 equals to 4, so that equals to 1/4. From that last statement that we're assuming about x of I equaling I equaling 1. Okay. So because of the identically distributed nature, so since x1, x2, and so forth are identically distributed, here's what we can say from what we have above. So, then for any Q element of J, we have the probability that x of Q is equal to 1 equals to 1/4. So for all the random variables that we have in our sequence, the probability that one of them is equal to 1 is equal to 1/4. The probability that x sub q equals to 2, that's going to be 1/4. The probability that x sub q will be equal to 3, that's equal to 1/4. The probability that x sub q equals to 4, that's going to be equal to 1/4. And the probability that x sub q equals to, I'm going to call it z, equals to 0 for all z element of the natural numbers where z, with z being greater than 4. So note x sub q is greater than 0, okay? Greater than for 0 for every the output values are always greater than 0 for where you have a chance for that output value occurring, a non-zero chance. Okay. Thus, we can apply the corollary to the compound random variable identity. And namely, what we could say then is the probability that S of n is equal to 5. That was our problem. What that's equal to is 1 over k, this is k, so 1 over 5, the expected value of n. So I'm going to write down here is 1 over k, so this is k, the expected value of n times the sum as j runs from 1 to k. Here this was j. There was alpha sub j, which was the probability that x of 1 is equal to j. And then times the probability that s of m minus 1 equals to k minus j. Okay, what was m minus 1? Well, m was a random variable that was independent of the x sub i's, but had that probability relationship with n. And here we're assuming that n was Poisson, so we know m minus 1 is also Poisson with the same parameter. And that parameter, I think, was 4 for us. So that was our formula. So let me write that down with some particulars for this problem. Please forgive me. Okay, so here's what we get. So the probability S of n equals to 5, so 1 over 5. The expected value of n was 4, I think, in our problem. And then sum as j runs from 1 to 5. That's the k. Here it was j alpha sub j times the probability that s of n minus 1 is equal to k, which is 5 minus j. Okay, so that's equal to 4/5 times, okay, so it would be 1 times alpha sub 1. What's alpha sub 1? Alpha sub 1 is the probability x of 1 is equal to 1. Well, that's 1/4. Times the probability that s of m minus 1 is equal to 5 minus 1. That's 4. Plus, okay, this is j equals 2. So it's 2 times alpha sub 2. What's alpha sub 2? Alpha sub 2 is the probability x of 1 is equal to 2. That was 1/4. Times the probability that s of m minus 1 is equal to 5 minus 2. That's 3. Plus, so here would be 3, that's what j is. Alpha sub 3, that's probability x of 1 is equal to 3, that's still 1/4. Times the probability that s of m minus 1 is equal to 2, plus, now it'd be 4 times alpha sub 4, that's probability that x of 1 is equal to 4, that's 1/4. But the probability that s of m minus 1 is equal to this will be 1, and then plus, here we have 5 times alpha sub 5, that's the probability that x of 1 is equal to 5, well that's 0, times the probability that s of m minus 1 is equal to 5 minus 5, that's 0. Okay, that's what I have. All right, so we want to find these individual items, these probabilities, so that we can have just this arithmetic type of statement, just numbers involved. And so even though this is 0, this is an iterative type of process. So I'm going to need to know, turns out in this type of problem, what the probability of that s sub m minus 1 is equal to 0. Well, by our corollary to the compound random variable identity. This is probability here of m minus 1. This is probability that m minus 1 is equal to 0. Okay. So remember what we said was m minus 1 is going to be Poisson with parameter lambda, so that's lambda equal to 4 in this problem. So this is going to be equal to e to the minus 4, 4 to the 0 over 0 factorial, so I think it's just e to the minus 4. That's what I get. All right, that's correct. All right. I need to know what the probability that S of m minus 1 is equal to 1. Okay. All right. So note the probability that S of m minus 1 equals to 1. Well, we have to use the corollary to the compound random variable identity n. And this will be 1 over k, so it's 1 over 1. The expected value of m minus 1. Sum, if j runs from 1 to whatever k is, well, that's 1. Then it would be, here it would be j times alpha sub j. And here I would have the expected value, the probability of S sub, well, here are indexes m minus 1, which was playing the role of n in our general statement for the corollary. And here, this is going to be, instead of m minus 1, it's not going to be the same random variable. It's going to be, I'm going to call it m sub 1 minus 1. So m sub 1 has the relationship to m minus 1, the same that m had the relationship to n. So that's m sub 1 minus 1 equals to, it's k, which is 1 minus j. Okay, so what is this equal to? This is equal to 1, and what's the expected value of m minus 1? Well, m minus 1 was going to be Poisson with parameter lambda, and then this problem has 4, so 1 times 4. And then here, this sum only has one term in it. It's 1 times 1/4. And the probability that S sub m sub 1 minus 1 is equal to 0. Okay, to calculate this, this is the same thing as the probability that m sub 1 minus 1 equals to 0. Now, m sub 1 minus 1 is related to m minus 1, but in the same way that m was related to n. And so what we have here is that this is going to be equal to the same thing as the probability that m sub m minus 1 was equal to 0, and that is it's going to be e to the minus 4. There's a little something hidden here, but because they're all Poisson with lambda equal to 4, this works out. In the next example we'll do, that hiddenness will be exposed. Okay, so that's what we have. This is correct. Now, the probability that S sub n minus 1 equals to 1, which is something else I need, using our identity, not 1, but 2, okay, using our identity. So here I made a mistake. This is e to the minus 4, but here we have, well, it's just e to the minus 4. That's right. But I had forgotten to talk about these numbers out front. So what is this? This is 1 over 2, expected value of m sub 1 times the sum as j runs from 1 to 2 here of j alpha sub j p of s of m sub 1 minus 1 equal to 2 minus j. This is going to be equal to 1/2, and this is going to be 4 And now we're going to have a sum, and the sum is going to be 1 times 1/4 times, here, the probability that S of m sub 1 minus 1 is equal to, it would be 2 minus 1 is 1, plus here we're going to have plus 2 times 1/4 times the probability that S of m sub 1 minus 1 is going to be equal to 0. Now, it turns out that these values, they're really different than what's here, but we can use the same ones because of the m's being Poisson. Okay? There's something hidden here, but I'm going to say that you can use the same ones as the values you had for just m minus 1. So let's look. Go ahead and mark what this is. So from our previous work, because we're dealing with Poisson, this is equal to 2 times 1/4 e raised to the minus 4 plus 1/2 e to the minus 4, and that's equal to 3/2 e to the minus 4. Now, the probability that S of m minus 1 equals to 3, that's going to be equal to 1, so I'm using the corollary again. This is 1/3, that's the k. The expected value of m minus 1, which we know to be 4, so I'm just going to write that down. Well, let's write it down. Expected value, m minus 1. Sum, if j runs from 1 to 3 in this case, j alpha sub j times the probability of S of m sub 1 minus 1 equal to k, which is 3 minus j. This is going to be equal to 1/3, here this is 4, times, this is going to be 1 times 1/4, and then the probability that S sub m sub 1 minus 1 is equal to 2, plus, this is going to be 2 times 1/4, times the probability that S of m sub 1 minus 1 is equal to, this is going to be j is 2, so it's going to be 1, plus, this is going to be 3 times 1/4, times the probability that S of m sub 1 minus 1 is going to be equal to 0. Okay. Look, to calculate this, we really should use the compound random variable again. But what I'm going to do is, because everything is Poisson, it works out to be the same thing as the probability that S sub m minus 1 was equal to 2, which we just had calculated. So this ends up being 4/3. Here, this is 1/4. That's that part. And I said it's the same thing as this. Didn't have to be, but it is, okay, because of the Poisson and the facts we have about Poisson random variable involved in this situation. So this is 3/2 e to the minus 4 plus, this is 2/4. Here we had done this before, probability of Same thing as S of M minus 1 equaling to 1, which we have found to be e to the minus 4 plus, this is 3 fourths, and then this guy is e to the minus 4. And so when we compute that, we end up getting, okay, this ends up being 13 over 6 e to the minus 4. So if you do the calculations, that's what you get. Let's just check that out. So this is 4. So this is 8. So 3 eighths, 3 eighths and 4 eighths, make 7 eighths, 7 eighths, 7 eighths, and that's 13 eighths. Okay, and so this 4 and that 4 will cancel. Well, the 13 eighths cancel, leaving the 2 in the bottom. And 2 times 3 is 6. Yeah, that's what. We also needed the probability that S of M minus 1 equals 4, using that corollary again. 1 over K, that's 1 over 4, take the value of M minus 1 times the sum as J runs from 1 to K, that's 4, J, alpha sub J, probability of S of M sub 1 minus 1 equaling to K, which is 4 minus J. Okay, this is going to be equal to 1 4 times 4 times the sum. So this is going to be 1 times 1 4. Probability S of M sub 1 minus 1 is equal to 4 minus 1, that's 3. Plus, this is going to be 2 fourths, 2 times 1 fourths, times probability that S of M sub 1 minus 1 is equal to 2, plus, this is going to be 3 times 1 fourth, times the probability that S of M sub 1 minus 1 is equal to 1, plus, this is going to be 4 times 1 fourth, times the probability that S of M sub 1 minus 1 is equal to, this would be 0. And so here, what we end up getting, so this is just 1. So it's just this sum. And so what we get using this iterative process, we 1 4, so that's this 1 4. This guy we just found to be 13 over 6 e to the minus 4 plus, this is 1/2, or if you will, 2 fourths. And this part we calculated earlier to be equal to 3/2 e to the minus 4. This is plus 3 fourths. This guy we had calculated earlier, which was e to the minus 4. And then plus, this is 1. This guy we calculated earlier, or from work we had done earlier, this is going to be e to the minus 4. And so if you compute this, what you end up getting is 73 e to the minus 4 over 24. If I'm denominator 24, that's what you get. And so it has this iterative process, as I said, but there's something that's a little hidden. That's our answer. But there's something that's a little hidden in this problem. And that has to do with computing these guys. Some of the technical work that's involved I'm not showing. And it turns out to be exactly what it was for M minus 1. The probability that S of M minus 1 was equal to 2. And that was because of the Poissonness of the compounding distribution. Okay. Having said that, let's look at what if the compounding distribution is binomial. Let's look at the fact of that. Oh, I didn't answer the problem completely. So that was that probability. That didn't complete the problem. I'm sorry. That was probability that S of m minus 1 was equal to 4. Oh gosh. So I'm sorry. So to complete the problem, the probability that S of n is equal to 5, that's going to be equal to 4/5 times 1/4 times 73 over 24e to the minus 4 plus 1/2 times 13 over 6e to the minus 4 plus 3/4 times 3/2 times e to the minus 4 plus e to the minus 4 plus 0. And if you keep working with that, what you'll end up getting is your answer is 381 out of 120 times e to the minus 4. Oh gosh. I'm sorry, I made a mistake. So I hadn't completed the problem. All right, so that's the answer to the example that we were doing. Now, here's the fact. It says as follows. It says let n be a binomial random variable with parameters R and P, not N P, R and P. Let M be a random variable such that the probability that M equals to N is equal to N times the probability that N equals to N over the expected value of N. Then, M minus 1, here this statement is true for N equaling 1. Little n equaling 1, 2, 3, forever. Then, I'm going to say something about n minus 1. Is a binomial random variable with parameters so it's R minus 1 and P. That's what we want to prove. Okay, so here's proof. Okay, we're going to assume the hypothesis. We're going to let N be a binomial random variable. With parameters R and P. All right. Then the probability that M minus 1. Okay, let's also assume. Suppose probability that M equals to N is equal to N times the probability that N equals to N over the expected value of N. Okay, so we want to show N minus 1 is binomial. So we need to show that its PMF has the right form. So the probability that m minus 1, remember that probability that I just wrote, that was true for, let me just write this down. That's true for n equals 1, 2, 3, and so forth. So let's go back now. Probability that m minus 1 is equal to n. Okay? That's the same thing as the probability that m is equal to n plus 1. So I'll write it in this way because I know something about n. I'm sorry, I know something about m that's related to n. And so that's the probability, that's the same thing as n plus 1, or the probability that n equals to n plus 1, over the expected value of n. I know that n is binomial, and so this ends up being n plus 1. Here, the probability that n is equal to n plus 1, remember that would be r, that's the parameter that time we did. Choose n plus 1, then it would be p to the n plus 1, and then it would be 1 minus p to the r minus n plus 1. And then the expected value of n is nothing more than r, and here that's the number of times we did it, and the probability of success is p. Okay, that's what it should be. All right, just checking my work. Yeah, that's right. That's exactly right. Okay, this is equal to, so n plus 1 over r times p. Here, I'm going to rewrite this as r factorial over r minus n plus 1 factorial. And here's the n plus 1 factorial. Here is the p to the n plus 1, 1 minus p to the r minus n minus 1, or r minus 1 minus n. Okay, so here we have some cancellations that occur. So n plus 1 cancels with this n plus 1 factorial. R factorial and this r cancels. So here's what we're left with. We're left with r minus 1 factorial, because the cancellation there. Here, this will be r minus 1 minus n, if you will, factorial. This n plus 1 cancels with the factor of n plus 1 and the n plus 1 factorial, leaving just the n factorial. This p cancels for one of the p's here. We're left with p to the n, and here it's 1 minus p to the r minus 1 minus n. So I'll group the r minus 1 together. If you will, that's r minus 1. Choose n, p to the n. That's 1 minus p to the r minus 1 minus n. That is the PMF of a binomial random variable with parameters r minus 1 and p. So I'm going to write that down. And that will conclude the proof. So n minus 1 is binomial with parameters r minus 1 and p. That's what we said, so that concludes the proof. Okay. Last thing I want to do during this lecture is I want to do an example. It's a little bit more complicated than the previous one. I'll go through all the details. So here, let n be a binomial random variable with parameters R and P. And S of n be a compound random variable where S of n, of course, is equal to the sum as I run from 1 to n of x of I with the sequence x of 1, x of 2 being a sequence being a sequence. What kind of sequence? This is a sequence of independent and identically distributed random variables. Well, I'm going to write more than that. Being a sequence, we want to be able to apply that corollary. So it's a sequence of non-negative integer values identically distributed random variables with n being independent of the sequence x of 1, x of 2, forever. And so here we let P of x of 1 equal to j be represented by alpha sub j. And so here's the question, the directions. Find the probability that S of n equals to 3 in terms of alpha sub j, R, and P. Okay. So in our problem, let me look back. So it was binomial, n was. Okay, that's good. We know that. So our previous work is going to come into play with the corollary for the compound random variable identity, as well as the previous factor. So here is our solution. Okay. Now the probability, so I'll write down why am I doing this. So by our corollary, the probability that S of n is equal to 3. It's going to be 1 over 3, expected value of n, and then times what? The sum is j runs from 1 to k, k is 3. So it would be j, alpha sub j, and then here I need a little bit more room. Probability that S, and then it would be m minus 1 is equal to, what would it be? 3 minus j. I know that's not very well written, but that's what it is. Okay, let me expand that. Okay, so what does that equal to? That's equal to 1/3. The expected value, m was binomial with parameters r and p. So rp times 1. That's j. 1. Start off. A sub 1. Okay, A sub 1 is what I got. And this is the probability that S of m minus 1 is equal to 2 plus 2 times A sub 2 times the probability that S of m minus 1 is equal to 1 plus 3 times A sub 3 times the probability that S of m minus 1 is equal to 0. Okay, that's what it is. All right. Fantastic. So I'm going to find these 3 probabilities. Iterated process here, using that corollary, a little bit more difficult than the previous example because when we had Poisson random variables involved, we could just use our previous work. But here, with a binomial, they don't have the same parameters. There's something that changes. So here, I'm going to say no. The probability that S of m equals to 0, that's the probability. It shouldn't say m, it should say m minus 1. That's the probability that m minus 1 equals to 0. Okay. What do I know about m minus 1? It is a binomial with parameters r minus 1 and p. So what would this be? This would be r minus 1 choose 0, the p to the 0, 1 minus p to the r minus 1 minus 0, and that's just equal to 1 minus p to the r minus 1. Yes, I got one of them. I got to hit this one. Okay, now, the probability that S of n minus 1 equals to 1. We use the corollary again. So this is 1 over k, that's 1. The expected value of m minus 1 times the sum, as j runs from 1 to 1, so on one thing here, of j alpha sub j, and then what is this? This is times the probability that S, now what we do is we form a random variable that has the right probability relationship between m minus 1 and itself, so itself and m minus 1. So I'm going to call m sub 1 minus 1, as I did in the previous example. And this is supposed to be equal to k, which is 1 minus j. So this is equal to, well, this is 1. Here, this is r minus 1 times p, that's the expected value. Here, this would be only one term. It would be 1 alpha sub 1. And now, this is the probability that S of n minus 1, 1 minus j. The j is 0, so this is the probability that S of m sub 1 minus 1 equals to 0. Okay, so this is not m minus 1, it's m minus 1, it's m sub 1 minus 1. Okay, so this is r minus 1 times p. Now what do I know? Well, m sub 1 minus 1 has the same probability relationship with m minus 1 that m minus 1 that, if you will, I should say m sub 1 has the same relationship with m minus 1, that the same probability relationship that m had with n. And so this m sub 1 minus 1, since this is going to be binomial with parameters r minus 1 and p, this is going to be binomial with parameters r minus 2 and p. And so this probability is going to be 1 minus p to the r minus 2. You do the same work, so it'll be r minus 2 choose 0, p to the 0, 1 minus p to the r minus 2 minus 0. So you just get this. So rewriting that, this. Alpha sub 1. You know what? All I did was, so R minus 1P, I forgot something. Yeah, it's so easy to forget things. So what did I forget? I forgot the alpha sub 1. Alpha sub 1, this guy was 1 minus P to the R minus 2. Okay, so that was the S of M sub 1. All right, that's good. Now the hardest one. The probability that S of M minus 1 was equal to 2. We're going to use that identity, that corollary. Compound random variable identity. This is 1 over K, it's 1 to 2. Expected value of M minus 1. Here this will be the sum. J runs from 1 to 2. In terms. So J, alpha sub J, probability that S of M sub 1 minus 1 is equal to K, which is 2 minus J. So this is equal to 1 over 2 times the expected value of M sub 1, that's M minus 1, that's R minus 1 times P. Now, this will be times 1 alpha sub 1, the probability S of M sub 1 minus 1 is equal to, will be 1 plus 2 alpha sub 2 times the probability that S of M sub 1 minus 1 is equal to 0. All right. Now the probability, so I need two things, this thing and this thing. Now the probability that S of M sub 1 minus 1 equals to 0 is the same thing as the probability that M sub 1 minus 1 equals to 0. That's by the corollary to our fact. Okay, what's M sub 1 minus 1? Well, M sub 1 minus 1 is going to be binomial with parameters. This one was parameter R minus 1 P. This is R minus 2 P. So this was equal to, I think, yeah, it's R minus 2. That's right. So this R minus 2, I can just go ahead and put that in. So it's 1 minus the probability R minus 2. I didn't make a mistake. That's what that is. All right. So, looking at our work here, the probability that S of M minus 1 equals to 2. That's equal to, it's 1/2 R minus 1 times P times 1 alpha sub 1 probability S of M sub 1 minus 1 equal to 1 plus 2 times alpha sub 2 times 1 minus P to R minus 2. How do we handle this? Now, the probability that S of M sub 1 minus 1 equals to 1, we use the identity again, the corollary to that identity. And so this is equal to 1 over 1, the expected value of M sub 1 minus 1, times the sum. As J runs from 1 to 1 of J alpha sub J, probability of S of M sub 2 minus 1, where M sub 2 is related to M sub 1 minus 1, with the same probability nature. And this is equal to K 1 minus J. that's equal to 1, the expected value of m sub 1 minus 1, that was a binomial random variable. M sub 1 minus 1 was a binomial random variable with parameters r minus 2 and p. It was r minus 2 times p. Okay, and then there's only one thing in here, and that's going to be in this sum. That's going to be 1 times alpha sub 1. So alpha sub 1 times the probability that S of m sub 2 minus 1 is equal to 0. That's equal to, okay, so here we have r minus 2 times p times alpha sub 2. Here, this is the probability that m sub 2 minus 1 is equal to 0. Okay, so here, remember, m sub 1 minus 1 was binomial with parameters r minus 2 and p. So this is going to be binomial with parameters r minus 3 and p. So what I did here is 1 minus p to the r minus 3. So I forgot things. So it's r minus 2 alpha sub, where did this become alpha sub 2? It's not, it's alpha sub 1. I made a mistake. Alpha sub 1. So it's r minus 2 times alpha sub 1 times p times, here it's here it's 1 minus p to the r minus 3. That's what I get. So, what I find for the part that I was looking for is the probability that S of m minus 1 equals to 2. That's where I was working. And that's going to be equal to, here's what I have. I have is equals to 1/2 r minus 1 to p times alpha sub 1. And I just found the probability that S of m sub 1 minus 1 equals to 1. It's this. So it would be r minus 2 times alpha sub 1 times p times 1 minus p to the r minus 3. Make sure I hadn't made a mistake. Yep. Plus 2 times alpha sub 2 times 1 minus p raised to the r minus 2. Okay, that's that part. So, the probability that S of m equals to 3. It's the 1/3 RP times. Okay. Let me look back. I won't make a mistake. RP. So it's okay, so it would be alpha sub 1, and it was S of m minus 1 equal to 2, which I just found. So this is alpha sub 1. This part right here is 1/2 r minus 1 p times alpha sub 1 r minus 2 alpha sub 1 p times 1 minus p to the r minus 3 plus 2 alpha sub 2, 1 minus p to the r minus 2. So it's alpha sub 1 times 1/2 r minus 1 times p times this quantity. Okay? So that's that bracket ending. Okay? All right, that's good. Then it would be, so 1/3 times this, okay? And then plus, all right, so let me back up. Let me look. It's 2 alpha sub 2. So I'll write down 2 alpha sub 2 times. Okay, so it's probability that S of m minus 1 is equal to 1. We did that. Let me find it. Okay, so what that was it's R minus 1 times P. It has an alpha sub 1. Alpha sub 1
r minus 1 times p times 1 minus p to the r minus 2. So that's still inside this bracket. Okay? Plus, then there was a 3, and so it'd be alpha sub 3, and then it was times, let's see, the probability that S of m minus 1 was equal to 0, we found that to be 1 minus p raised to the r minus 1. And so that bracket is ended with that. That's my answer. You can multiply things out and simplify this somewhat, combine like term possibly, but that's the way that I'm going to leave the answer. And so that ends this example. And that concludes what I wanted to do for this video lecture. Thank you very much for your time and patience.